Good morning. Let me start. So today I continue the presentation of the quantization of the scalar free field using the path integral method. So we consider the scalar free field quantum. And as I already stated, usually the method of path integral is rather called the functional integral, because we integrate our functions rather than just histories or paths. Okay. So I'm going to discuss most of the discussion will take place for the Euclidean theory. Mostly for convenience, and at the end we are going to discuss what's happening for the physical theory at real time. So, in the Euclidean theory, my Euclidean space-time is just the plane, and therefore we have Euclidean points are labeled by some x mu equal 1 to d. We have the standard Euclidean signature, and a field is a function phi of x, which is real. And the Euclidean action for a field configuration is just the integral of a space-time of 1/2 of d mu phi squared. Here we don't have to care whether the index is up or down because it's the same signature as plus m squared over 2 phi squared, where m is the mass of the particles that appear in the spectrum of the theory. Okay? And what we expect is to define a functional integral, which is of this form, with some Euclidean measure of a field configuration of exponential of -1 over h bar the Euclidean action times when you compute observable correlation function, we have to add some quantities corresponding to field operator that I'm going to discuss later. Okay. And as I remember, it's the I factor and the signature of space-time will appear back when we are going to do this. Okay. So I already stated that it is convenient, in fact, if we want to repeat the steps we did for the quantum mechanical particle, to discretize time, and in order to have a system with a finite or a discrete number of degrees of freedom, to discretize space. So I'm going to introduce first a finite Euclidean time and periodic, both for simplicity and because it corresponds to studying the quantum scalar field at finite temperature. And I'm going to introduce a finite space. So instead of having a space-time which is R, I consider a space-time which is a torus. So space-time is a torus. So X belongs to a torus of size, let's simplify, L times L times L. So this is the period in time, this is a period in space, but for simplicity I consider both of them. This is space and this is Euclidean time. Okay? So that's what is called an infrared cutoff, because it changes the physics at large distance. Yes?
Why do we consider space to be periodic?
For convenience. So this is for finite temperature, and this is for convenience with derivation. Okay. At the end, we take L. We can take this goes to infinity, and this goes to infinity, which corresponds to temperature equals 0. So our field lives in a box. Okay. Now, I've seen what we have to introduce. It's convenient to introduce what's called an ultraviolet cutoff by considering that instead of having a torus, I have a grid, so a lattice. Okay, with mesh epsilon equal delta t equal delta x. So again, for convenience, I introduce the same ultraviolet cutoff or ultraviolet regulator, the same minimal distance in the time direction and in the x direction. But here the time is the first direction. So the time is delta tau, is corresponding to x0, and this is x1 up to xd minus 1. So consider for simplicity mu going from 0 to d minus 1. And then the Euclidean action for such a field on a discretized spacetime, if we want to define properly a functional integral over this discretized field, you have to replace in the action the derivative by finite differences. So we have to replace d mu of phi by something which is, let's say, a finite difference operator, delta mu of phi, which is basically, if you have a point here, I, labeled by I, which is a set of indexes I up to in minus, I'm sorry, d minus 1, which are integers. So, and to this point, I have xi, which is I, the vector, times epsilon. This is the corresponding vector on the lattice. This is phi of xi plus e mu minus xi, minus phi of xi divided by epsilon, where e mu is a unit vector, e mu equal unit vector in direction mu. So this is a vector of the form 0, 1, 0, and this is a mu index. Okay, so this is a finite difference. Then the discretized action, you just take this, you replace the integral by a sum of a site. So the Euclidean action for a field configuration, if you want to discretize, is just the sum over the sides of the lattice, sum over I, in the lattice. You have a volume element for each point on the lattice, which is the volume of the elementary cell. So it's epsilon to the power d. Okay. And then you have this term, which is just sum over mu from 0 to d minus 1 of delta mu phi at the point xi squared with a factor 1/2. Plus, here you just sum over the sides, so this is m squared over 2 phi of xi square. I hope the notation are clear. So this is a discretized action, Euclidean action. Okay. And if we follow the rule that we did for the particles, the measure is the discretized measure dE of phi discrete is just a product over all the sides on the lattice, of course, of the standard flat measure of the real variable phi, so d phi of xi. So at each point, you have a field phi, which is an independent variable. So at each point, you have a phi of xi. And we had a normalization factor, which for the quantum particles, if I remember well, was 2 pi h bar, the time interval element, divided by the mass. Okay? And in this case, one has to be a bit careful, because what corresponds to the mass is a term in front of the kinetic of the time derivative element. You see? So the mass is epsilon d minus 1. And the time interval is epsilon. So the mass here is something different. It's not the mass of the field. There is no concept of a local mass of a field, of a quantum field. M here, mass here. M is the mass of the one particle state in canonical quantization. It's something that's going to, we hope to see this, the mass of a one particle state, emerge from functional integration. So the final result is, if I am not mistaken, there is still the 2 pi h bar, because there is a 1 over h bar here. And we have here an epsilon to the power of the dimension of space-time minus 2. Okay. That's the result. It comes from the fact that we have an epsilon on the numerator and an epsilon d minus 1 on the denominator. D minus 1 because it's the dimension of space. Okay. So the final result is epsilon equal d equal to. And so you see that something happened if space-time has dimension 2, okay, so that I'm going to describe later. Okay. So this is the path integral. So take this as a definition on the path integral. We have a discretized action. We have a discretized measure. And so if we have a finite lattice, a lattice that has a finite size and a finite mesh, we integrate over a finite number of variables. So this is a finite integral. So this integral. And it is a Gaussian integral. So this is. So the functional integral, in this case, is a Gaussian integral, which makes calculation in this path integral or functional integral formalism easy for the free field. Okay. Now, I think we can, at that stage, before starting calculating physical quantities with this path integral, we can make a very useful remark. We can discuss what is the connection with statistical mechanics. Okay. You can see that the discrete path integral can be viewed just, you have a dictionary. You can imagine that you have a lattice. You have a d-dimensional lattice. Well, here, cubic or hypercubic. And on this lattice, you put coupled harmonic oscillator. So at each side, I have an oscillator which fluctuates like that. So it's a one-dimensional oscillator. So if you take just along a line, you have a side. On each side, you have an oscillator that oscillates like this in some direction. It has some, so you have a, see. It has some, so you have a spring here. You have a spring here. The spring has some stiffness constant in this direction. Let's see. Here you have a stiffness constant that I'm going to call K2. It's local. And in addition, you assume that those oscillators are coupled in a linear way. So it means that you have additional springs. Linearly. You have additional springs here between neighboring couplings along the links with a stiffness K1. Okay. So you have a local stiffness K2 here and a stiffness here along the links K1. Okay? And you are interested into what is the statistical mechanics of this system at thermal equilibrium. So let's call the distance between the spin and the origin, let's call it a spin SI. So we have SI, which is a continuous spin variable. So it's real. It belongs to R for each site at each site. I, which belongs to this lattice N. So I denotes the integer position. Okay? So we have a configuration. It's a set of value for this continuous spin variable. Now, what is the energy of a configuration? The energy of a configuration is a set of the spins, energy. This is going to be the sum of the energy of the local term. It's sum over the sides I of, well, kappa 2 divided by 2 SI squared. This is the first term. And then we have a sum over the links of the lattice. E equal IG for nearest neighbor interaction of K1 over 2 SI minus SG squared. That's it. Because that's it. Okay. So this is a local term. And this is the interaction, the coupling, linear coupling term. Okay, is it clear? Okay, so now consider that we want to study the statistical mechanics of this system at finite temperature. So I take this system of linearly coupled harmonic oscillator on a lattice, and I want to compute its statistical properties at finite temperature. Something that you did in the statistical mechanics course. That's a classical system. These are classical spins. They are not quantum. It's like continuous Ising spin. The difference with the Ising model, in fact, this model would be the Ising model if the spins could take only value plus or minus 1. So the only difference between the Ising model on a lattice is that the spin is continuous. Okay? So at finite temperature T, and I'm going to call this temperature, the partition function for this system is just the sum over all spins configuration, possible spins configuration, of exponential minus 1 over kBt times E of S. But this sum over configuration here, configuration is just an integral because the spins are continuous. So this spin is just a big integral product over the sides of dSi. Okay? And so you see that this big integral that defines the partition function for this system, okay, let me just, has exactly the same form than this term. Yes?
What exactly is SI?
What?
What exactly is SI?
SI is just the position of the spin, the excitation, the value of the spin variable.
Yeah, so it's 1/2 or -1/2. No.
No, it belongs to R. We have continuous spin. So that they can take any value between -infinity and +infinity. It's just a model. It's a model of statistical mechanics. Okay?
You're not talking about the position of the spin. You're talking
No, well,
about
when I spoke about the position, I'm sorry. I said I take the position of the value of the spin along this side. So this was a bad terminology. Forget about the position of the spin. Consider that S is the value of the spin. SI equals value of the spin variable for the spin SI, which is located at site I. Okay? So if this was an Ising model, at each side you would have a spin, a local spin, taking value plus or minus 1. Here it's exactly the same model, except that the spins take value between -infinity and +infinity. So instead of having discrete Ising spins, I have continuous spins. That's the only difference. So it's an Ising-like model. But with continuous spins, classical. Okay? So the position was a bad terminology. In fact, I used this language because, in fact, this model is also equivalent to a model of elastic lattices. An elastic lattice, where then this would correspond more or less to the position of the spin, to the position of atoms. So you have a lattice and you deform. So it's also, you can also formulate a model of classical phonons with this kind of lattice, this kind of model. And in that case, the spin variables will correspond to the displacement of each atom. Okay. Okay. So the point is that there is a dictionary. You know, mathematically, this partition function is the same thing that this functional integral product over I of d phi I, phi of xi, with some factor times exponential of -1 over h bar times se of phi. Simply because you can make a dictionary because this integral, between this integral and this integral, you see. The position, so the dictionary is the following. Between the model of the left, which is the model of statistical mechanics, and the model of quantum field theory. Okay. The dictionary is at Euclidean space-time. Space-time, which is 1 plus d minus 1 dimensional, becomes my lattice space. The space in which my model, my classical model of statistical mechanics is defined. You see. The field phi in this integral becomes SI. So it becomes the local or microscopic order parameter. If this was an Ising model, this would correspond to magnetization. So SI. So phi at the point x labeled by the index I is the local spin variable SI. This is the dictionary. What else? You see, the constant of the model, K1 and K2, will correspond to some parameter in the action, in the Hamiltonian. So the K1, K2, the parameters, K1, K2 correspond to parameters in the Hamiltonian, in particular the mass. Okay. M. Okay. Now, what is most important is that the 1 over h bar here corresponds to the 1 over kBt. And E, the energy of a microscopic configuration, corresponds to the action. So the energy of the configuration, the energy corresponds to the Euclidean action. Okay? And kBt corresponds to h bar. Because that's something which is on the denominator in the Gibbs factor in front of the energy or the action term. So you see that if the temperature is small, this corresponds to a model where h bar is small, a quantum theory where h bar is small compared, for instance, to the mass. So we've seen that thermal fluctuations here are small, while quantum fluctuations here are small. So if we continue the dictionary, I should have done that. If we continue the dictionary, the next blackboard, okay, you see that thermal fluctuation should correspond to quantum fluctuation. Okay. And finally, an important difference. Our system, on the first blackboard, I assume that it was defined in a finite box, my path integral. So I had an Euclidean time period. Let's call it tau. This corresponds to the first L. Okay. Which corresponds to describing a quantum field theory at finite temperature with the famous relation T over h bar equal beta. This corresponds to the size of the system, of the spin system, in the first, or if you want, in the first direction, in one of the directions. That's it. So if we consider this spin system in a finite box, this corresponds to considering a quantum field theory at finite temperature and in a finite space box. Okay. But the temperature of the quantum system, let's call it beta equal 1 over h bar T quantum field theory, is not the same parameters as the temperature of the system here, the spin system. You see. Those are two completely uncorrelated parameters. The temperature of the quantum field is related to the size in the time direction in periodic time, while the temperature of the statistical system is in correspondence with h bar. So you should not confuse the temperature of the quantum system and the temperature of the statistical system. Okay. So that's the end of the dictionary. And that's a very important dictionary because it's particularly simple for this very simple system of linearly coupled lattice of oscillators, or of lattice of Ising model with continuous spins. But the dictionary is general. You may introduce more complicated coupling between spins, non-linearities in the couplings. They will correspond to another quantum field theory more complicated than the free quantum scalar free field. Yes?
So so there is a correspondence between statistical mechanics and QFT, and if I, for example, change the temperature in my QFT a bit, and the size there is going to change a bit. Well, what happens exactly if I change the temperature here? Because you say it's linked to h bar.
It's a dictionary between two mathematical objects.
Huh? Yeah. So what happens in the QFT if I change the temperature in the statistical mechanics?
It means that simply that you consider that, well, expressed with respect to the other quantities of the problem, h bar has to be considered larger.
What does that mean?
Well, it means that, well,
h bar is a constant, so like your couplings change? Or?
Well, of course, h bar is a constant in our physical universe. But first, when we do math, we can play with models where everything is the same except the h bar parameter and see how the physics change when you change h bar.
You have a formula for h bar.
Yeah, we have a formula. Yes. I think that there is nothing different with, for instance, the gravitational constant, which is also a dimension-full parameter. But you can, when you study gravitational physics, you may start to consider, some charged objects. The charge is fixed, so they interact with the Coulomb force, and you want to compare the Coulomb force with the gravitational force. Then the natural thing is to take the equation for interaction between these objects, keep the charge fixed, and tune G. It's the same.
And how exactly do you get an equation between 3 and h
bar? It depends on the problem we are. Okay, we'll see example, I think, later. So, but that's at that stage. Just consider we have a dictionary, and this is a dictionary. I'm going to compute now some physical, more physical objects. But you have to keep in mind this very important dictionary, which is a classical statistical model in d dimension, in some sense, is in correspondence with a quantum field theory in d-1 dimensional space and relativistic, so that it has a one time direction. You see? So for instance, let's consider a 1 + 1 dimensional quantum system. Well, let's say a one-dimensional quantum system. If you were at the colloquium yesterday, you heard a lot about quantum spin chains. So you have a one-dimensional chain. On each side, you have a quantum spin, not a classical spin. Okay. Quantum spin is described by an operator. Here at each site I, you have a spin, but it's an operator. So this is a quantum system. And it was discussed that some quantum spin chain were in correspondence with a two-dimensional statistical model, which in the case mostly discussed by the speaker was a two-dimensional Ising model. So this is an example in a non-trivial case, because the two-dimensional Ising model is non-trivial, of a correspondence between a one-dimensional quantum system, an extended quantum system, and a two-dimensional classical system. Okay? So, okay, good. Okay. So, now I've defined, well, formally I said this is a functional integral we have to compute. I explained that there is an analogy, there is a dictionary between statistical mechanics and quantum field theory on very general background. Of course, you have to make this dictionary explicit when you compute physical quantities, when you want to try to solve the model, but you expect this general correspondence. And now I'm going to use functional integral to compute some of the physical quantities you have studied in the QFT1 course. So I'm going to discuss what are the properties of the two-point green function, suppose also correlator function, correlation functions, in the scalar free field, using path or functional integral methods. You'll see that it's very easy to compute this. Okay. So I'm going to compute the following object. Now I consider my scalar free field in infinite space, infinite time, and I want to compute the two-point function, which is defined in this way. So I note the two-point function expectation value, that's a bracket, of the products of two fields, phi located at a point x1, phi at a point x2. So I have my space-time, my Euclidean space-time, this is Euclidean, and I have a point x1, I have a point x2, this is somewhere in RD, which is Euclidean space-time. And in a path integral formalism, for instance, this corresponds to simply to compute the ratio of the following path integral, exponential minus 1 over h bar, the Euclidean action for the free field, times the value of the field at the point x1 times the value of the field at the point x2, and I normalize that by the partition function, which is e dE of phi, exponential of minus 1 over h bar, SC of phi. Okay. That's just by analogy with what we did for quantum mechanics, where we're considering, remember, expectation value of products of two-position operator. That's just, so take this as a definition. Okay. This is what I call the two-point correlation function in the scalar free field in Euclidean space-time. Here, this is in Euclidean for the Euclidean theory. Okay, so we want to compute this object and to study its property. Well, for the scalar free field, that's very easy to study because, as we have seen, this is a Gaussian integral. This is a Gaussian integral. Okay? Because SE of phi, well, you can integrate it by part oops, the kinetic term. And you can rewrite this as integral over space-time of 1/2 and phi times the operator minus the Laplace operator plus m squared times phi plus boundary terms. This boundary terms vanishes if the space-time is periodic. So under this form, the fact that you see that the Euclidean action is a quadratic form in terms of the field variable. And delta is a Laplace operator. Delta is d over dx mu times d over dx mu. That's a Laplace operator. Okay. So this is a Gaussian integral. So what we are computing here is, in fact, the expectation value of the product of a Gaussian random variable. And this is called the second cumulant of this random variable. Okay. So we just have to use the properties of Gaussian integrals. And one of the basic properties of Gaussian integral is that, let's consider a matrix that I'm going to call K, a matrix. Let me consider an n by n matrix, which is symmetric and positive. So I call it KAB, which is symmetric and positive. So K is a matrix, so those matrix elements are KAB. Okay? And let's compute the following Gaussian integral. Integral product from A equal 1 to n of a random variable that I'm going to call just d phi A, exponential of -1/2 phi A KAB phi B. So this is exponential of -1/2 the scalar product of the vector phi with this form. Okay, that's a typical example of a Gaussian integral. Well, this is known to be the determinant of the matrix K divided by 2 pi to the power -1/2. That's a standard result of Gaussian integral. Now, if we want to compute the analog of this is a finite dimensional Gaussian integral. If you want to compute what is the expectation value of phi A, phi B for two chosen A and B, which is given exactly by this integral. This is the expectation value of this with this measure. It is known that this is the inverse, this is the matrix element AB of the inverse of the matrix. Inverse of K. Okay? I can show you that, but I hope you have seen this integral. Okay. And, well, how is it? So let me call this GAB, the matrix. This is a matrix element of a matrix G, okay, which is the inverse of K. Okay, so the fact that it is the inverse of the metric K means simply that GAB times K, well, let's say KAB times GBC, if we sum over repeated indices, is delta AC. That's the definition of the inverse. Definition of the inverse. Okay. So we just need to apply those basic integrals to these integrals, where now, instead of having an nk, instead of being an n by n matrix, k now is minus delta plus m squared. It is a differential operator. Okay, so it's an operator that acts on function on space and transforms them into another function. It's a linear differential operator because it maps a function phi into a function k times phi, which is minus the Laplacian plus m squared of phi. Okay. It acts on the function in space. Okay. So we expect that the corresponding expectation value here, phi of x1, phi of x2, which with my notation should be some function g that I'm going to call g of x1 and x2. Okay, so this function should correspond to the matrix element of the inverse of the k operator, which is a differential operator. So this should correspond to what is called the value of the kernel of the operator minus delta plus m squared of the inverse of this operator. Okay? Which is often denoted, you take this operator and you take its expectation value between two states, so that's a bracket notation of quantum mechanics. Okay. Here we are not doing quantum mechanics, it's just a standard notation for denoting the kernel of this operator. Okay. So what is this function? Well, this function is the inverse of this object. So this function should satisfy the differential equation. If I consider minus the Laplacian plus m squared, but applied to the first index of g, which corresponds to x1. So I consider, so g should be a function of two positions, and I consider the Laplacian operator with respect to the first position. So I multiplied g by k, which means that I applied this operator with respect to x1 to the function, which is a function of x1 and x2. Okay? And what I should obtain is a kernel of the operator, which is the identity. Consider the identity operator on acting on the space of function. What is the identity operator acting on the space of function? We write this here. What is the identity operator? It's to a given function, it adds phi. So what is its kernel? Its kernel means that the identity acting on phi, which is a function of x1, should be equal to dx, well, let's say of d of y. The kernel of the operator, I'm sorry, x and y, applied to the function y. This is the analog of this function. If you have an operator, if you have a general operator, let me call it O, acting on function phi, so to a given function phi, its associated function psi equal O applied to phi, it means that its kernel is defined by a function O of x of 2 point O of x and y, such that when you integrate over y and you apply to the function point y, what you get is psi of x. This is the definition of the kernel. Okay? So for this, for this to give phi of x for any function phi of y, it's clear that the kernel is the identity. It's just a delta function of x minus y, Dirac delta function in d dimension. Because of course, we are in d dimension. Okay. So the kernel of the identity operator is just the delta function. So this is the equation which must be satisfied by the two-point function. You recognize the Klein-Gordon equation with a delta function on the right. Yes?
Does any operator have a kernel?
Let's say you have to open a book on the theory of differential operator and functional analysis. Not all operators have a kernel, but there is a large class of operator, which I think is called kernel class or trace class operator. I think class operators have a kernel. Okay. And you'll notice already on this example that in general, a kernel is not a function, it's a distribution. Okay. In general, kernels are distribution. So that's, for us, it will be a technicality, but in math, it's very important. Okay. And of course, an operator is defined by the space of function on which it acts. So I haven't specified on which class of function I'm acting. But in fact, you should specify whether you are acting on a class of L2 function, which are square integrable. Well, in our case, since the operator involves differential, it has to be a space of function where you have constraint on the norm of the function and of their derivative. So in fact, in practice, this is properly defined in some class of what's called Sobolev space. But I won't go into these technicalities. OK. So let's go back to this. So we want to solve this function, which is a function that you probably have already met either in statistical mechanics or in quantum field theory. The best, so what is the solution of this equation? The solution of this equation is quite simple, especially if you go in Fourier space. So first, well, you can notice something. You can notice that because of translation invariance, that's the problem. Translation invariance. We expect that g of x1 and x2 will be just, in fact, a function of one variable x1 minus x2. Remember? Remember, x1 and x2 are points in d-dimensional space. So it should be just a function of the difference between the position of the 2 points. And one can prove that. Okay. Good. Now, so I'm going to denote this by g of x in general. Okay. So now we can define the Fourier transform of that. This equation by denoting g hat of k. This is integral d dx e minus I k dot x. These are vectors. This is k dot x times g of x. Of course, k dot x means k mu x mu. This is we are in Euclidean space, so in fact the fact that we have upper or lower indices is not important. Let's write it like that. Okay, so this is the definition of the Fourier transform. We have the inverse Fourier transform. And when we deal between this equation in Fourier space, we get an equation that relates g hat of k. So what is the Fourier transform of the differential operator minus second derivative Laplacian operator plus m squared? This is just k squared plus m squared, where k squared is k mu, sum over mu. Okay? So in momentum space, in the Fourier transform, this operator is diagonal. Okay? And what is the Fourier transform of the Dirac function? It's just the constant function. One constant function. So this is the Fourier transform of this equation. which means, of course, immediately that G hat of K is just a Lorentzian in reciprocal case, and first important result. And then, of course, that G of X, so X now is X1 minus X2, is integral d dk over 2 pi to the power d times ei k, the dot products of k with x divided by k squared plus m squared. Okay, I think you probably have already seen this function. This is the Fourier transform of a Lorentzian distribution. Centered at the origin in d-dimensional space. Okay? Yes?
So the variable that we're taking the Fourier transform of, is that x1 minus x2?
Yes. Yes. Here I'm using the notation that x is x1 minus x2 because...
So we're assuming that the Green's function only depends on x1 minus x2?
Yes, I'm assuming. But you can...
because of what translation invariance of the Hamilton?
You can prove that. No, but simply, you see, this operator is invariant under translation. You see, minus delta plus m squared commutes with translation. Because translation are basically represented as d over dx mu, acting on function. So it's obvious that this operator commutes with this one. And the right-hand side is invariant under translation. So the solution has to be invariant. Okay? It's just a matter of symmetry.
Okay, so we're inverting an operator. Doesn't the operator, isn't 0 an element of the operator? Of the spectrum of the operator?
Does it?
Isn't 0 an element of the spectrum of that operator? And if
no.
So, how can you invert it?
No, it's not 0, because these are the eigenvalues of the operator, k squared plus m squared. You see? Because eigenstates are e I kx, and eigenvalues are k squared plus m squared. The eigenstates are plane waves, and the eigenvalues are k squared plus m squared. This is always positive, because if m is positive, this is positive or 0, and this is different from 0. So,
but if I take away that I, then I get...
Huh?
You say that the eigen functions are e to the power I kx.
Yes, this is a block wave.
E to the power kx.
Yeah, but take k equals 0, it has eigenvalue m squared.
But why not e to the power kx instead? That's
because it's not normalizable.
Neither is a plane wave.
This is not normalizable. Plane waves are normalizable.
How?
These are the one.
How can you normalize a plane wave?
If you want to do things very properly, you study this operator in a finite box with periodic boundary condition. So in a finite box with periodic boundary condition, there are plane waves that are periodic. You just have to quantize the momenta k. This doesn't work for exponentially growing or decreasing. So these are the eigenstates in the properly defined space of function. Okay? So if you want to be sure, so this is periodic, this is admissible. This is not admissible. Because you cannot make periodic function out of pure exponential, of hyperbolic cosine and hyperbolic sines. But you can make a parabolic function out of sines and cosine. That's nothing more than that. Okay? Okay, so let me go back to this because I want to study to give you what are the properties of this object. Okay. So this is the two-point function for the free field in position space. Okay? And this is a two-point function in momentum space. Okay, it's very simple. Okay, so now you open your books, handbooks of mathematical functions, and you find, if you like, that this is related to some modified Bessel function for the second time. So it's a function, in fact, of the argument absolute value, the norm of the vector x times m. Then you have a second kind Bessel function. And then you have a normalization, which is 1 over 2 pi modulus of x divided by m to the power 2 minus d divided by 2. Okay, so I don't ask you to learn this explicit formula by heart because I don't know it either, but that's okay. So now let me discuss the properties of this function because that's important. What are the physical properties? Of this function that we can extract from, for instance, this value? Well, first, what are the properties? Let's call the infrared or large distance properties. How does this function behave when the points are very far apart? Well, it's easy to see that g of x, in this case, behaves as exponential of minus the norm of the vector x, the distance, times m. So as long as m is positive, or let's say, there is an exponential decay at large distance. We are in Euclidean space, distance at distance. Okay, exponential decay. Now, what is the ultraviolet small distance behavior? That's where things become interesting. Because, so what's the behavior when x, so this is the behavior when x goes to infinity. Okay. So what's the behavior when x goes to 0? When the 2 points are very close here. Well, the explicit result is that, well, there is a coefficient that I'm not writing to it, is that we are in quantum field theory, remember. So dimension is larger than 1. The dimension, we have space and we have time. So dimension is 2 or 3 or 4, etc. Okay? And you see that when x is very small, what counts here is a region where k is very large. Okay? And when k is very large, you can neglect the mass. And you can check then that this integral is divergent for large k. So you expect some singularity at a small distance. Okay. So we can do the calculation, and what you find is that g of x behaves when x goes to 0 as x to the power 2 minus d with some constant, let's call it AD. Okay, so this is the case if the dimension of space is larger than 2. Okay, so you see that there is a singularity it goes to infinity when x goes to 0, because d is larger than 2. And if d equals 2, you should say, OK, there is no problem because this is a power 0, but in fact there is a log. And it's minus 1 over 2 pi log of x. OK, so in both cases, you see that there is a singularity. It diverges when x goes to 0. Goes to 0. So this two-point function is singular at short distance. Okay. And this is something which is new. This happens for quantum field theory. This doesn't happen for quantum mechanics. You can, of course, define the same correlation function in quantum mechanics. In fact, you have studied, you have calculated it in the tutorial. In quantum mechanics, non-relativistic, you can define the same object, and g of x is, in fact, just exponential of minus m times x. You see. So it's a function that, as a function of x, it's decreasing, but then it's finite here. Well, I think there is a 1 over m, because you still expect some problems when m goes to 0, but this is basically this. Perhaps there is a factor of 2, I don't remember. Okay, so this is finite. In a quantum field theory, as a function of the modulus of x, this decays exponentially at large distance, but this goes to infinity at the origin. Okay. Okay, you'll find the value of this constant in the notes, or you can compute it by yourself. At that stage, it's not very important. Okay, so I still have 20 minutes, so let me just discuss two things about this. First, I would like to return to the physical time. See, because I computed this two-point function starting from the theory at Euclidean time with Euclidean action. Okay, so that's the calculation makes sense. We use the properties of Gaussian integrals. But of course, we have to check that. Well, I think I can use the middle here. We have to check that what we did makes indeed sense. So we would like to go back to real time. And check what this is. So back to Minkowski and real time. So up to now, everything is defined with respect to position that belong to the Euclidean space-time. So in fact, when I write the position of x, the first component of a position vector in Minkowski space is Rd in Euclidean space. Rd is Euclidean time, and the other are the position in space. And if I make the transformation tau equal it, So starting from the tau axis, I go to the physical axis by a big rotation in this direction. Okay, so I write that instead of having a real tau, I have an imaginary tau, which corresponds to a real t. Then I expect that the corresponding t is a component of a vector in Minkowski spacetime. Vector point in Minkowski space, I can write 1d minus 1. Okay. But now we have to treat separately time and space. Okay. So now let's go back to this function. We have seen that g of x is integral d dk. So let me write this as integral d tau, integral d minus 1 of x times 2 pi to the power d times exponential of I and kx. I'm sorry. No, I'm sorry. I'm going to integrate over momenta. So I have momenta in Euclidean space that I'm going to call Ka, which are going to be K0 and K. And this is integral over K0. This is integral over K. Ei K0 tau plus K times x divided by K0 squared plus K vector K squared plus m squared. So this is the definition of the propagator in Euclidean spacetime. I just separated the first component for the space component in Euclidean space. Of course, this makes no difference. But now, I want to see what happens when I make a Wick rotation. I go from real tau parameter to imaginary tau. Okay? So one has to be a bit careful. So let me, in fact, reverse this and make a rotation to make things a bit more clear. So this is the tau axis. This is the time axis. So t is, of course, minus I tau. This is notation. Okay? And so initially, I want to go to a point, to a value of tau here, to the imaginary value of tau here, which corresponds to t real. So of course, in this integral, this is a time complex plane. In the K0 plane, see this is K0. K0 is a variable, and here I integrate K0 from minus infinity to plus infinity. So this is for tau real. This is the integration path on K0 that is taken in the Fourier transform. You see. Now, imagine that I start to plug on my Wick rotation so that tau now is somewhere here. Okay. So when tau is somewhere here, you see that it gets an imaginary part. Imaginary time part times I means there is a real part in the exponential, and somewhere the integral, if I continue to integrate from minus infinity to plus infinity, the integral is growing at some point. So that's not what we have to do. But this is an integral on a contour in the complex plane of a function which is considered as a function of K0, an analytic function. So we can generalize this integral to the complex K0 plane. Okay? And in the complex K0 plane, what we have to do is that we have to rotate the contour of integration starting from the origin in the opposite direction. Let's see, I have an angle here, theta, in order to compensate the phase in tau by the opposite phase in k naught. So when you start a Wick rotation, you have to rotate the contour integration of k naught in order to get still a consistent result. That's a mathematical trick. Okay, good. And so at the end of the calculation, let's see, when, let me have a red. When you end up here, where tau is purely imaginary, so that the physical time is real, you end up with a contour of integration like that. In k naught variable, we go from plus I infinity to minus I infinity. Okay? And so and then these integrals becomes an integral from k naught from plus I infinity to minus I infinity. So if I just change our variables by defining k naught equal minus I w, where w is real when k naught is imaginary. Okay. This axis is my axis of integration over omega. Okay. So Euclidean time, real time, Euclidean momentum, if you want, physical frequency. It's going to correspond to well, it's a pulsation, if you want. It's 2 pi times the frequency. Okay. And then I just make a change of variable. So then what becomes g? So now g, when tau is imaginary, I rewrite it in terms of t and of x. This becomes, so instead of integrating from I infinity to minus I infinity, I rewrite this as an integral over d omega from minus infinity to plus infinity, and there is to be going a factor minus I because I make a change of variables, and minus because I am changing the order of integration from plus infinity to minus infinity to minus infinity to plus infinity. I get a factor exponential of I omega t plus kx. Okay? This is this factor. There is, of course, a factor, a factor dx, integration over dx. I've done nothing to the x. Dk. I made nothing to the k. Okay? There is a 2 pi here, and there is a factor 2 pi d minus 1. I have not touched to the integration over the x. I have no need to, because k is still real, x is still real, so there is no problem. And this becomes, k naught squared becomes minus omega squared plus k squared plus m squared. Okay. So this is just the analytic continuation to real time of this formula for imaginary time. Okay?
Yeah, you say I omega t plus k dot x. Should there be like an I and a possible minus there?
There is a I here. Here there is no I.
No.
In the exponential.
Yeah, in the exponential. Say
I'm sorry.
omega t.
Yeah. No, I'm sorry. This is Yeah. It's the same height. Yes. Okay. Yeah.
Should there be a minus sign because it's Minkowski?
Not with my notation. Check. Maybe they should, but there isn't. That's with my choice of notation. That I am pretty sure.
You can always change the.
Okay. Okay. So this is just the analytic continuation in time of G of omega. I'm sorry, of K of tau and X. This is just an analytic, if you want, weak rotation. Okay. Okay, so this looks very much like a propagator you got in quantum field theory 1. But now, of course, there is a subtle point. This integral has a pole at omega equal plus or minus square root of k squared plus m squared. Okay, you see, this denominator vanishes simply because this is real for real k naught, but this has a pole here. And this has a pole here at k naught equal plus I square root of k squared plus m squared, and at k naught equal minus I square root of k squared plus m squared. Okay? Yes?
Okay, so there's two k zeros there. There's one in the exponent and one in the denominator.
Yes?
And the one in the denominator there, k0 squared becomes minus omega squared.
Yes.
So omega is like plus or minus I k0.
Yes.
And then in the exponent you have I k0. Tau switch.
No, because I rotated. I changed both t and k naught. I change tau in it, and I change k naught in minus I omega. So that in any case, k naught t is the same thing as omega. K naught tau is the same thing as omega t. You agree? Because I times minus I is 1. Okay, so you get this formula, and you get a possible ambiguity because you may have poles. But now, of course, basically, the poles are somewhere here, you see. But since you rotate things, you have the poles here, you have a pole here, you have a pole here, and you know that since you rotate like this is the contour of integration you have to take.
Sorry, why do we know? Why do we know
Because
about the contour?
Because I start from a contour of integration when tau is real, with this contour of integration over k naught. When I start to rotate tau, I start my weak rotation, I had to rotate the contour of integration. And when I ended here, I end with a contour of integration that is like that.
So, yeah.
Okay, you see?
Yeah.
So, the omega contour of integration, let me write it once again, in the omega plane. Now, in the frequency, real frequency plane, omega plane, in the omega plane, okay, this is real omega and this is complex omega. This integral has poles here and here, and my prescription of a contour of integration over omega is this one. So now, if you go back to the QFT1 course, you recognize that this integral is nothing but of Tx is nothing but the Feynman propagator for this vector. This is the Feynman propagator in position space. Well, in space-time, in Minkowski space-time. Okay. And you know that this object corresponds simply in terms of matrix element of operator to the vacuum-to-vacuum matrix element of the time-ordered product of two fields operator, the field operator phi, so this is the phi operator at position 0, and the phi operator at position x, with x equal t and the position vector x. So through a Wick rotation, this is a functional integral two-point function obtained by Wick rotating the result we get in Euclidean spacetime, and it agrees with the results of canonical quantization. We get the Feynman propagator, the correct causal combination of advanced and retarded propagator. Okay. So, functional integrals, quantization, agrees with canonical quantization. We have checked that what was true for quantum mechanics works for the quantum free field. Okay. Okay, so finally, I think I wanted to go back to this divergence and to explain where this divergence is coming from by showing you some snapshots of numerical simulation on the Gaussian free field, on the free field. But I think it would require, well, showing the pictures plus some explanation would require about 10 minutes. So I think it's better to do it tomorrow, the beginning of the lecture. Okay? Unless you really want to see that. I think it's better. Yes?
So we are Wick rotating, which basically means we have a path over the real line, and we're going to move our path analytically.
Yes.
So we need to check two things. One is that the region we're moving over is analytic.
Yes.
And two is that the boundary term, like what happens to the boundary terms. We have something like e to the power I variable times variable.
No, you are right. In fact, you are right. I was a bit.
One of the
I was putting. No, I was putting some detail under the rug. In fact, of course, when you make this rotation, you have to check that going from there to there. These are not important. They are not. Why? If you walk properly.
Why?
Well, that's.
I mean, you're basically walking on an infinite circle.
Yeah.
For a variable e to the power I, that variable. So at some point, it's going to blow up.
No, because here you rotate. This is a function of tau. This is just a convenient an integral representation of a function of tau.
So what's tau?
Tau is a time parameter, so complex time parameter. So well, if you prefer, take this definition of the integral by Wick rotating the contour of integration over K naught as an explicit construction of the analytic continuation of this function from real tau to complex tau. So if you take this formula with this choice of contour, you can check, and without caring about what's happening at infinity, take this as a definition. Then you can show that the final result is analytic in the plane. And that's all what we need.
I mean, you literally have boundary terms which are
No.
e to the power I times the variable.
I'm doing
One of
math.
the two
I'm
sides
doing
of it.
math. I define, by this construction, the analytic continuation of what I constructed for Euclidean time to
So you're changing
Real time.
tau as you go, or
Pardon?
you're changing tau as you go, or what's
yes,
happening there?
yes. I'm making an
That's-
analytical. I have a function which is
That's not
defined.
Cauchy anymore.
What?
How do you rotate? What is a Wick rotation?
It's a mathematical operation. It's analytic continuation.
operation?
It's not a physical operation. It's a mathematical
What
operation of analytic continuation. Okay? For a function.
Well, what's the operation?
The operation is this is the example. I made an explicit calculation. I constructed the Wick rotation. I have a function that I defined
You're
here.
drawing a line.
What?
But you're just drawing a line. What exactly are you doing? Because you're changing that and you're using.
I'm not drawing a line. I am making an integral. I'm making an integration over one variable. I'm integrating over a contour, and I'm choosing my contour in the complex plane.
Yes, you have a fixed contour, which is just a real line.
No, I'm choosing the contour. I'm showing by this choice of contour, this integral still exists. It exists there. It exists there. It can be analytically continued. So the integral over each intermediate step makes sense.
So your contour is the 8.
My contour here, when tau is here, I choose this contour. When tau is here, I choose this contour. When tau is here, I choose this contour. And I check that when using this prescription, the results I get is an analytic continuation, is analytic as a function of the complex parameter tau defined in this rule plane is an analytic function. And that's all what I need. So my math makes sense. Okay?
Maybe to you.
Huh?
Maybe to you.
No, it makes not only, no, I'm not the inventor of this method. You know, this calculation is decades, half a century old. But just don't, no, I don't want to upset you. Just, you're right to ask the question. It's not completely obvious, but if you check
You're doing
all the
things that
steps.
you've never seen, and I have no clue how to do that, and you're not explaining how you're doing it. You're changing tau, and at the same time your contour. What does that even mean? You're making an analytic continuation of what?
You see, here I am integrating over a variable k0, a function which is an analytic function of k naught. So, if I start from integrating over k naught like that, I am free to choose any contour of integration.
Sure.
Okay?
Okay.
As long as it behaves properly at infinity.
Yeah, but it doesn't.
It does if you choose this receipt.
No, if you also change tau at the same time.
Yes.
If you're not changing tau at the same
No,
time.
but no, I agree. But when I change tau, I have to change the contour accordingly in order for the integral to make sense. That's the only choice you have. Check.
I don't know what check means.
Read, no, do the calculation.
What's calculation?
Check that the result is consistent, and check that if you make another choice, the calculation does not make sense. I don't. That's all what I can say. Okay, let's stop there. But we can continue to discuss if you like. But I think that's.